So, vector addition here. Determine the magnitude of the resultant force that is acting on the screw I and its direction measured clockwise from the x-axis. So there's these two ropes connected to this eye bolt, and that's cool and all. The eye bolt, we'll see it, that kind of, you can add these two vectors together, and that's what the eye bolt would see, is really the summation of those two. And, that one pulling down is pulling stronger than the one pulling up. So, there are these various angles. This one over here, the top one is 30 degrees from the vertical. This one is 65 degrees from the horizontal. So they're close in their, basically their symmetry about the x-axis. They're not exactly the same, but their values are much different. So I can guarantee you that resultant, if we add them together, is coming over here somewhere, right? All right, well, let's just take a look at it. So now I have drawn this triangle rule bit, okay? Look back at this problem. I have the 5 kilonewtons here acting at 65 degrees from the x-axis, okay? So let's see how I built this. Here's my 2 kilonewtons at 30 degrees from the vertical. That's my first given force. And then I took the 5 kilonewton force, which was acting down here, and I moved it up there to build my triangle, right? So this 65 degrees right here is actually the 65 degrees from the horizontal that was in the given problem. Okay? I'm just taking this vector, sticking it up there. All right. So the angle work in this is kind of messy, so that's the fun of graphical vector addition. I'm trying to step you through this. All right, so we know that angle and we know that angle. Okay? Since we know 30 degrees here, this extension of this axis, or whatever you want to call this line going up here, that would make this 30 degrees. Not sure I need that, but it's cool. I like to draw everything and see what I can see. So it is 90 degrees from vertical to horizontal, duh, all right? And then this is 30, so that makes this angle right here 90 minus 30, or 60 degrees. So that is useful, because this is 60 degrees. This given value here was 65 degrees. That tells me that this angle of this triangle here is going to be 180 degrees minus these two other angles. So 180 minus 60 minus 65 is 55 degrees. We have to take the real world and turn it into a triangle. Once we have the triangle, we can analyze the triangle using theoretical math. And at the end of the day, we're going to take those numbers back from the triangle and apply them to the real world. Okay, so this is getting this is that triangle angle that we care about. Okay, notice it was not one of the angles that was given to you, which is so often the case. So now I'm just taking this and drawing it over here so you can see it as a triangle as opposed to all this other angle stuff, right? So I have 55 degrees here, which is what I calculated. And then I have this angle A over here, which I'm just calling A because why not? That's how we, that law of sines and cosines was kind of built in the version that I gave you in these slides. So we don't know this value yet. I'm kind of spoiling it, I suppose. Let's do the law of cosines and calculate it. The way that we would calculate it, because this would just be FR here, unknown at the time, but it would be equal to 2 kilonewtons, which is this side, squared, plus 5 kilonewtons squared, minus 2 times 2 kilonewtons times 5 kilonewtons times the cosine of the angle opposite the one we're trying to find. So this is FR, so this is cosine of 55 degrees. We take the square root of that whole bloody number, and we get 4.187 kilonewtons, which is the value, the length of this side, if you will, the force value that we're looking for. Okay, that is our resultant. So if you were the joker that said, I can just add these two numbers together, I got 2 kilonewtons and 5 kilonewtons, that would give me 7, right? Well, look, the resultant is nowhere near 7. It's not even as big as this component over here because of the way that this problem is built. That's not always the case. It happens to be here. And that's also part of the reason why we're going to have this ambiguity case pop up here that you'll see in a second. Okay. This angle here, A, you can see it. I drew this to scale. It's greater than 90 degrees. That's why we're going to have a problem. Okay. I'm going to run the law of cosines again. And the reason I do that is because of that being greater than 90 degrees. You might say, how do I know that's to be the case? I mean, am I magic? Well, I mean, you don't always know it. I drew it to scale, so it was kind of obvious to me. Like I said, a great way to check it would be to run the law of sines and find each angle, not just A, but also find this angle over here, add this angle and A and 55, and you would find out if it works or not. I believe this angle over here was 23 degrees. You could check it at home, but 23 plus 55, okay, is 78 degrees. And then if I ran the law of sines, I think it actually was 78. So 78 plus 78 was 156. And that's not equal to 180 if I sum up all three of these angles. So that's why that law of sines business didn't really work. So if you run the law of cosines and solve for A, you get 102 degrees. All right. But note, plug in, like I said, if you do the law of sines here, again, and I don't have it written here, but we could do it easily, right? Just solving this by law of sines, I would take 4.187, divide that by the sine of 55 degrees, because that's the angle opposite. I get 5.111. That's going to be equal to 5 kilonewtons divided by the sine of A. Okay, so I could, by rearranging everything, once I do all that and solve for the sine of A, I would get that sine of A is equal to 0.9782. So I could take the arc sine of that, and I would get 78.01 degrees. So that's where the law of sines would give me 78 degrees. Well, if I take the sine of 78 degrees, I get that 0.978. If I take the sine of 102 degrees, I get 0.978. That's the ambiguity case I'm talking about. Okay. So our law of cosines did not fail us. We got 102 degrees. Okay. That is this angle here. That's still a theoretical triangle angle, and that's great and all. That's not what we're looking for. I said, what is the direction measured clockwise from the x-axis? So we just found this big angle here. But what we're looking for is this. So what do I need to do? Don't I know that angle? Yeah, it's that 60 degrees. So I can just take 102 minus 60 and I get 42 degrees, and that's a clockwise angle from the x-axis, and that would be our answer. Okay? That's great. I know that ambiguity stuff is kind of messy. It only happens when, well, I'll say it only happens. I'm pretty sure it only happens when the components are greater than the resultants, like it was in that last case, which can happen, but it doesn't always happen. But again, the good thing about the graphical method is you see it. You see the things drawn, and you can see that resultant, and that's great. I actually strongly recommend, instead of that method, you use the x and y components. The main reason is because it's not that often, well, I mean, we do have a lot of cases where there's two forces acting that we need to add, but it's also very common that we have 3 vectors that we need to add, or 4 vectors that we need to add, or 5 vectors that we need to add. And the graphical method becomes very slow if you have those. So the x and y component method, it might have more numbers in it, but the method is still always the exact same amount of steps, which is nice.